Okay, now that we have configured the model and the initial and grid file, we're going to run the first example, which is the initial gravity waves. So let's go into our ROMs example directory, the shallow 2D, and let's begin again by making sure that the initial condition files and the grid are the exact ones that we want for the initial gravity waves. So we have the two files here, the SW asterisk. So let's open the grid file here, and if we go here towards this is the beginning of the file. This is what we saw before. If we now go towards the end of the file, we are going to have that the f parameter is going to be a constant, which is the f plane, which is what we want, and the topography is going to be a constant as well, which is flat topography. So this is good. So I'm going to create these files. First, I'm going to run the grid again for the initial gravity waves, and I'm going to run the initial condition file again. Okay, so that's done. And on a separate windows now, on a separate window, let's use this one. Okay, let me just okay, on a separate window, I'm logged in on the master again. I'm going to go in the example directory. I'm going to go in shallow 2D, and I'm going to open the run model PBS file. I'm going to make sure that all the parameters are correct. So I have the ROMs example shallow 2D, which is the directory where I am right now. I'm going to have a log file. I'm going to use the binary which is contained in this directory in the bin folder, and it's called shallow 2D ROMs, and the input file we just defined before in this directory. So with these files in mind, then I'm going to submit the job by running qsub. Okay, I'm going to do qstat. And I can see now that since the cluster is up again, it's running, and it's a status of running. And this job shouldn't take more than about a minute. Okay, so let's do qstat again. As this is going, let's go back to the MATLAB window here. Okay, and let me do an ls here. And what I prepared here for you is, in addition to the two files to create the grid and the initial condition, there's some examples of how to plot the solution for these waves example that we will perform. So in particular, let's start with the f-plane waves, which are the one that we just configure in the model. And let's look at this example, VI f-plane. So in this example, I load the grid associated with this example. I create a new figure. And here I just put the name of the history and averages files. Okay. Now the default ones are his and av.nc, but when the run is finished, I'm going to move those history file and averages file to a different name so that I can store them and not be overwritten by the next examples that I'll be running. So so I'm going to wait for the example to finish. Let's see, in fact, if it's done. No, it's still running. Okay, so just wait a second. And then here there's a whole bunch of examples of how to plot or make a movie of the transient adjustment with the propagation of the initial gravity waves, and then also to make a movie of the slow component. So in this case, you're plotting, the solution from the average file instead. Okay, and then there's other diagrams and plot that I will show you in just a second, but they're all containing here. So I'm not going to go in the details of this script, but you are welcome to study in more depth this script to understand all these plotting functions, some of which could be very handy for other things. Okay, so I'm just going to close this WQ, and I'm just going to run this script as it is, and it's just going to run me through these examples. But before I do that, let me go and see whether the run is completed. Okay, qstat tells me that the run is completed. I do an ls, and I find that there's a PBS log file and a pbs.error file. Let's do ll. The PBS error file is 0, so the run went well. There's a log file. We could do tail -300, which is a command to look at the last 300 lines of the log file. And the run seems that it's completed and there's no problem. It wrote all the histories and so forth. So now if we do ls of his.nc, we find that this file exists. Also the average file should be there. Okay, so I'm going to move these now into the his underscore fplane .nc. So I'm going to save this file so that the next examples I won't lose it. I can still plot the solution, and then I'm going to also move the average file in there. Okay, so I've done this, and right now I'm showing you how I'm doing and running the model, but the next demos I'm just going to show you the solution. Okay, so we have that, and now we can go back in our MATLAB and we can start plotting the solution. So this is a script. You'll open a window. I'm just going to enlarge it a little bit here. Okay, so now we're going to first look at the transient solution. So these are the output from the history file, and which is, you know, on every 4 hours. And so we should begin with a bump here, and you can see that now the bump is spreading, and as it's spreading you see this ubiquitous propagation of these inertial gravity waves, which spread all over the domain. And when they reach the boundaries, you see they also get reflected and come back into the domain. They also propagate along the coastal boundaries like Kelvin waves, even though it's not very, you can see it just maybe a little bit here. And but you can see that basically they're ubiquitous, and they become kind of a noisy part of the solution. Okay, so now we're going to do the same movie, but we're going to actually use the average file, which kind of filters a little bit by averaging in time, you know, the propagation of these waves. So this is the next movie. So in the average solution, we find our bump here in the middle. Okay, and you can see that the bump is kind of, you know, shaping itself a little bit because of the propagation of these inertial gravity waves, but it's mostly staying in place. And what's happening here is that there's an adjustment, the geostrophic adjustment is taking place. So this bump is becoming geostrophically adjusted. Okay, and so it stays in place with the geostrophic adjustment. Well, let's see let's also do another interesting plot now, which is we're going to take a transect across the bump in the x direction, and we're going to plot this transect as a function of time to see whether in fact this bump is actually moving eastward or westward or anywhere. And so this is what this next diagram is going to show. And let me shape the figure, and then I'm going to go back to the MATLAB window and press return. And so now I have this transect. This would be the western boundary, the eastern boundary, and in this axis we have time. So this is times in days, you know, about 180 days. And you can see that the bump is pretty much steady. It doesn't really move, it stays there. But you see all this noise associated again with the fact that we haven't fully filtered out the inertial gravity waves, because this is just a one-day average. If we took a longer average, we would have less noise in the solution. Now let's also plot the final state of the solution, meaning the sea surface height, the v and u velocity at the final state. So I'm just going to go back to the MATLAB window and press return. And so here now I have the u bar, the v velocity, the u velocity, and the zeta. And you can see that the zeta shows the bump, which is still in place. And associated with the bump, there's an adjustment of the u bar and v bar in geostrophic adjustment. And so here you see u bar, for example, it's negative and positive, which mean that, you know, the flow field is going in this direction, which is basically anticyclonic circulation around the bump. And in fact, you know, high sea surface height is usually associated with anticyclonic circulation in the northern hemisphere. And the v bar is also consistent with that, with negative velocities and positive velocities. So we have that this bump is in geostrophic adjustment. So this was the inertial gravity, is basically an adjustment problem to the bump with the radiation of inertial gravity waves on an f-plane with constant topography.